Hey, I'm Mr. Phil and welcome to my Simplified Odometry tutorial. The repository will basically have 3 files in it, and then there'll be a robot Java, a sample Autonmous Java, and a sample Teleop Java. Basically, you'll take these 3 files and drop them in your team code folder, and then you should be able to build the project. This is the robot class that goes along with my Simplified Odometry tutorial. It's reasonably elaborate. It's not that long, but I go into a lot of detail in this video. You don't really need to know what's going on inside this class if you just want to use the basic autonomous movement that I've shown in the Autonmous sample. It's also used a little bit in the Teleop sample that's in this tutorial. But honestly, if you just want to use it, go ahead. If you really want to understand what's going on, then please struggle through this tutorial. It's probably longer than you'd like, but that's because I go into as much detail as I think is necessary to really understand what's going on. So I hope you find this useful, and even if you don't use it directly, you might pick up a few tips on how to create your own robot class. If we have a look at the layout of this file, we define the robot class and specify a whole bunch of constants. So these constants really relate to your particular robot, how it performs. Do you have a heavy robot, a light robot? What's its odometry modules being used? Stuff like that. So all of these parameters are set up initially, and these numbers here just suit what we were working with, which was a standard Go Builder strafer chassis, really. Reasonably fast motors, 400 plus RPM. So depending on what you have, some of these constants may need to be tweaked. But basically, we have inches per count for the odometer, the odometry modules. Do we need to invert the odometry values based on the way they're mounted to the robot? Bearing in mind that what you need for this to work as is you need, when you push the robot forward, the axial odometer should count up. If it doesn't, you would set an invert to true here. When you push the robot sideways to the left, the strafe odometry module should count up. If it doesn't, you would reverse, you would invert it here. So you put a true here. So this true false here is set so that you end up with positive odometry counts in the forward and the left direction. After that, we have the various constants associated with the 3 controllers. In this tutorial, I use 3 simple proportional controllers to close the loop on the 3 axes that we're controlling: drive, strafe, and yaw. Sometimes you might use a PID controller, proportional integral differential, but in this case, a proportional controller is simpler and it's effective. And the reason that we can use it here is because even though we're only using the error in the position or heading to generate a request to the motors, those motors have closed loop control. So we're actually requesting a speed from the motors, and if the motors don't reach the speed that we want, they will increase their power to achieve it. So that means that even though the proportional controller may be just requesting a very small velocity, the motors will ensure that the robot moves like that. So it will close on the desired position or desired angle without the addition of an integral element in our controller, because it's already built into the velocity controller of the wheels. These constants that we're using here to initialize each of the controllers, I'll talk about them later when we actually talk about the controller, but suffice it to say that you can tweak each of your axes depending on your robot's performance. You can make it more responsive or less responsive to your heart's content. There's a few local variables. These ones are used to keep track of the current distance traveled in the drive and strafe direction and the current heading of the robot. We define 3 of these proportional controllers, one for the drive, one for the strafe, and one for the yaw. So these 3 elements here are what we use to actually achieve the motion, achieve the power that we then send to the wheels. We create motors, motor objects for the 4 drive wheels, and we create motor objects for the 2 encoders. Because the encoders are being plugged into motor ports, we need to treat them as motors, but we just need to read them basically, get current position on them. If you were also using the motor ports to actually run motors, I would recommend that you just create 2 more motor classes and just use them to send commands to the motors. Basically have an encoder variable and a motor variable and use them separately, as long as you don't issue conflicting commands like change the mode of one and expect the mode of the other one not to change. We also create an IMU object and a timer that'll help us out with some of our motion. A bunch of variables that keep track of the current heading and the odometer values. And one thing we need to know is we need to keep track of the turn rate of the robot, which comes from the IMU, and we use that to tell when we're manually driving, when the robot is physically stopped from a turn, we can use it to lock in the new heading. In initialization, this gets called straight away after the object's been created. It goes through and sets up each of the drive motors. We have a little helper function down below that we just pass it the name of the motor and whether the direction needs to be forward or reverse on that motor, and it creates the motor for us. This is a key point. This section of the code must be updated to suit your robot configuration so that if a positive command is issued to any of the motors, the wheels actually rotate forward. And the reason we can't predict exactly what your robot should have is because depending on your drive mechanism, it could be very different. You could be belt drive, you could be gear drive, you could be right angle drive, who knows? And just depending on where you put your gears and your bevel gears, it can reverse the motor direction. So as soon as you get a system up and running, you want to push the stick forward and make sure that all the wheels rotate forward. If they don't, you need to go back to this section of the code and flip the forward reverse logic here. This is where we attach to the encoders. You see the encoders are called, the encoders are called axial and lateral. These are for the odometry pods. Go back to the other video to talk about how the odometry pod should be set up. And once again, it's important that when you move in the correct direction, the encoders count up or down. And that's something we can set up in this upper section here when we talked about inverting the odometry, setting these to be true or false. We also go through and set up the encoders on for bulk reads, which will make the cycles faster. That's what's being happening in here. We also set up the IMU module using the new universal interface. We have to tell it which way the control hub is mounted to the robot. In our case, as long as it's mounted flat, we're good to go. It doesn't really matter which way it's pointing because we're only considering rotating it around the main axis. But if the control hub is up on its edge or sitting at a funny angle, then you may need to go into this section here and modify where the logo is pointing and where the USB port's pointing on the control hub to get the IMU orientation correct. We reset the odometry before we leave this initialization. And one of the things that are built into this code is the ability to turn telemetry on and off. So many of the functions have telemetry built into them. But if you don't want it wasting time on the display or taking up the display, you can just turn it off when you initialize this. Here's that little drive motor setup function that I talked about, where you just pass it the name and the direction, and it builds the object and then returns it. Notice it puts the puts the motors into run using encoder mode. This requires that you have the encoder cables hooked up. If you want to run this setup without encoders on the motors, you will probably need to add a little bit more control into the controllers. You may need to add an integral term into the proportional controller. So I would strongly recommend use the encoder cables and run these motors in run using encoders so that it's running on velocity commands instead of power commands. So now we come to the read sensor function. And given that the key reason for doing this tutorial is the odometry, it's surprising how little the actual odometry comes into this code. Most of where the code does its work is what it does with the odometry. But read sensors is called every Teleop cycle, or it's called repeatedly during autonomous while it's trying to do motions. And its job is to read any of the sensors that we need for odometry. So the key things here is first thing we do is we get the current position from the two encoders which are attached to motor ports basically. So we have the drive encoder and we have the strafe encoder. You'll notice we multiply it by either plus or minus 1 depending on whether we have the invert flag set. So these flags are based on which way your odometry modules happen to be pointed, and you just need to make it so that when you move forward or left we get positive values. So this gives us the raw odometry. which never really gets reset at any point, doesn't make any assumptions. It's just continually running, measuring position. But then what we do is we take the raw value and subtract the offset. Now the offset value is what gets reset regularly in order to reset the encoders. So whenever we want to reset the odometry back to 0, all we do is we record the current raw value into the offset value, and then in this code, when we subtract the two, we get how much we've moved from the last time it was reset. And we can do this. This is fairly simple, but we do it because we are assuming straight line, linear motion without any real rotation. It's an approximation, but it's generally a pretty good approximation in this situation. So drive distance and strafe distance are measured in inches, because there's a scale factor, in inches from the last time it was reset. And this is typically at the beginning of every motion. We reset the odometry modules, so drive and strafe distances gives us actual movement inches. We also read the gyro, and we do some offsets same way with the heading, so that we have a heading offset that we set to the current value when we zero the gyro, but that doesn't get done very often. That's only done at the beginning of Autonomous. And then at the end here, we have some telemetry, which when it's turned on will show you what's going on in the odometry. It's designed to make it so that you can verify that your odometry and your distances and your heading and everything are working as expected in the correct sense. You don't have to have it on once you're running. You can just turn it off and turn off the telemetry. But the first line is showing ODOM, which is basically our encoder readings. And they also have the offset subtracted from them. So these are the encoder counts since the last time we did a reset. So typically it's encoder counts since the beginning of the current motion. And these are in counts, and the AX and the lat is axial and lateral. So the first number is going to be forward and backwards encoder counts, and the second number is going to be side to side encoder counts. Then we have dist for distance, and this is going to actually be the calculated distance in inches. So it's really the same data, except it's scaled differently. So if you want to see how many inches the robot thinks it's moved in the current motion, just look at this line. Once again, axial and lateral. Finally, we also show heading information. We show the heading in degrees, and then we show the rate. So degrees, so the rate is going to be degrees per second. So while we're turning, this rate is going to show a significant value, and when we stop, it'll be pretty small. Then we return true. So once again, read sensors is the key element of measuring motion, and then the values of drive distance and strafe distance are what's used everywhere to actually then monitor and control and regulate the motion of the robot. And you'll see them show up in several places. So whenever you see the word distance, you know we're talking about movement in inches. Okay, so now let's look at the three main motion routines. Remembering we have drive, strafe, and turn to, and we'll just use these in sequence in Autonomous to move around the field. This is not the most elaborate way to do this. It's not the cleverest. It's probably not the most efficient. But once again, we're going for a simple motion to enable teams just to put together some fairly standard kind of autonomous routines. All right, so let's look at drive, which is the simplest. Drive moves us forward and backwards a certain distance. It tries to keep us on the line so we don't move sideways, and it locks our heading in so it doesn't rotate and steer off course. So how do we do that? Here's the function. It's given a distance, a power, and a hold time. Remembering hold time is the period at the end of the motion where once it's in position, or once it's gotten in position, we give it a little bit extra time just to refine its position and line up nicely. And this is optional. You don't have to use this if you don't want to, but if your robot's not real stable, this is a good way to get some fine positioning. So we take the power that we're passed, take the absolute value because we only want positive power for what we're doing here, and we reset the odometry. And we do this because we want the distance traveled in the X, Y directions to be 0 at that point. Because remember, we're moving in a single straight line, either sideways or forward and backwards. And so we can assume our starting point is 0, and then we're trying to achieve a distance based on that starting point. So in this case, the first thing we do is we set up the set points for the 3 axis controllers. Remembering that in each case, we're giving it a set point where we want it to go to and stay, so that then as we loop, it can determine how much power we should apply to achieve that set point. So we have 3 here. So we have the drive controller, and we give it the distance that we want to travel and the power, the maximum power. we have the strafe controller, and we give it a set point of 0, which means stay where you are in the strafe direction. If you move off to the left or the right, come back to that 0 position. So that's how it stays on the line. And then we have a yaw controller, and the yaw controller, we don't even give it a set point because we want it to just reset, but keep the last set point that it had. So it's resetting its time and its outputs and things like that, but it's not changing its set point. That's because the only time we change the set point is when we use the turn to command. So once we've set up the set points, then basically we go into a while loop that will keep running until we achieve our goal or until the end of the op mode. So here's our loop, and in our loop we're checking the end of the op mode, and we're also calling read sensors so that we get updated position information. So we really only have one command here to actually set the robot in the correct motion, and that is the move robot command. And here's move robot. So move robot needs 3 parameters: a drive power, a strafe power, and a yaw power. And we get those by calling the get output method of each of the individual proportional controllers. We pass it the current position. It knows its set point, so it gives us an output value. So in this case, we do that for the drive controller, the strafe controller, and the yaw controller. Pass that to move robot, and move robot is responsible for converting that into the 4 powers for the wheels. Once we've calculated those powers and sent them off to the motors, then what we want to do is determine whether it's time to leave this loop. And we do that by calling the in position method from the controllers that we're interested in. In this case, we want to make sure that our drive is in position, which means we've achieved the distance that we asked it to travel, and that our yaw is in position, which means that we're actually currently pointing at the right heading. Once we get in position, then we actually use our timer value to determine when we've stayed there long enough to let everything stabilize. And once we've been there long enough, we call break, which gets us out of this while loop, and that's the end of the motion. So we stop robot and then return from the drive function. If we're not in position, we just reset the hold timer, because that's its way of knowing that once we get in position, the hold timer is going to be 0, so it's going to count up to the hold time. So that's drive. And if we look at strafe, it's essentially exactly the same code, except drive and strafe are reversed, because instead of going forward and backwards, we're now going sideways. So if we look at how we set up our controllers, drive controller, which is forward and backwards, we put a set point of 0 in here, which means we don't want to move forward or backwards. And if we drift off of that straight line, the controller should bring us back to where we want to be. So if we drift forward an inch, the controller will bring us back an inch back onto the line. So it'll let us hold that line. The strafe controller is given the distance to be traveled, because we want to move 20 inches left or 40 inches right, and the power. Remembering that the distance is actually a plus minus value, plus to the left, minus to the right. We do a reset on the yaw controller just to set its timers and everything correctly, but we don't give it a new set point. There's no parameter here, which means it maintains the set point that it's had before. And the only time that controller gets its heading set is when we call turn to. We go into the loop again. Our move robot command is exactly the same, because we're letting the drive, strafe, and yaw controllers generate the outputs that we want. But then when we want to check to see whether it's time to go, we actually do an in position check on the strafe controller. So when the strafe controller says, "Yay, I'm in position," that means we've traveled far enough, and then we can exit out, or we can wait for the whole time. So those two are pretty similar. If we look at the turn to method, it's similar but actually simpler, because in turn to, all we're interested in doing is getting to the correct heading from wherever we are now. We don't care about strafing, we don't care about driving, because all we're doing is doing a pivot turn. So here, the first thing we do is we set the set point of the yaw controller. So we do a reset, we give it the new heading, and we give it the power, and that sets up, so now the yaw controller knows where it's meant to go, and then we go into this loop, and in the loop, in the move robot, we're passing in 3 values, but the first 2 are 0, because we don't want to drive, we don't want to strafe, all we want to do is rotate based on the get output value here. Once again, once it's in position, then we check the hold time, and if we've been there long enough, we exit out. So that's essentially the 3 drive functions, and they get used for Autonomous to do whatever movement we want to do. So now we need to look at some of the little support functions and the proportional controller class that we use to do that. So move robot is the primary function responsible for actually driving the wheels. And you see it's given 3 parameters, and these are axis motions. So we're taking axis motions, lateral, axial, and yaw, and turning them into wheel powers. So in this case, we pass the 3 axes in, and these are plus or minus 1 kind of numbers. We have 4 motor values: left front, left back, right back, and they are calculated by just summing or subtracting the appropriate axis values for each wheel. Once we've done that, we need to make sure that none of these values are bigger than the range, so plus or minus 1. And if it is, we need to normalize them, which means scaling them all down so that only one of them, or so that none of them above 1. So what we do is we find the maximum of all the absolute values. And then if that maximum value is greater than 1, then we actually divide all the values by that maximum, which means that anything that was, whichever value was the largest now gets scaled down to a value of 1, and all the rest gets scaled down by the same factor. Then we take those values and send them directly to the drive motors. Now, remembering our drive motors are in run using encoder mode, which means that the firmware will adjust the power levels to the motors to achieve the correct velocity. So if we give it a really small request, like 5%, instead of just sitting there and not being able to overcome its friction, it will actually kick up the power to the motor until it actually is moving at 5% of its full speed. So that's why we can get by with just a straight proportional controller on the axes, because our motors have closed loop PID control on them. And lastly, optionally, it will display all these parameters on telemetry so you can see what's going on. We have a stop robot command, which just sends zeros to all of the axes. And then we have some reset commands. In our case, when we want to reset the odometry or we want to reset the heading, we don't actually set them to 0. What we do is we read the current values. We use that as an offset. Then whenever we read it again later, we subtract the offset from it to get the new value. So that lets us reset the encoders without having to physically use the change the mode of the motors to stop and reset encoders, which could mess up a motor drive. So we just do all that stuff just as variables in code rather than going back and trying to reset the gyro or reset the encoders. So then finally we have the proportional controller. So this proportional control is used in 3 places to control our 3 axes of motion. And if you remember, we created 3 versions of this object at the beginning of the code. Here, a drive controller, a strafe controller, and yaw controller, and we initialized them with the values up in this area here with our constants. Quick recap here. So for each controller, there's these 5 values. The gain is what's used to convert the error into a power level. And so this is usually a small number because we're going from a error which may have 10 or 20 degrees down to a power that is somewhat less than 1. So it's going to be a decimal. If your robot doesn't seem to get places fast enough in terms of closing the final gap there, you may want to increase this. You can keep increasing it until your robot goes unstable. Unstable means it sort of bounces around the value that it's trying to get to. Once you see it go unstable, then you can lower that value down, and that might give you the best combination of time and accuracy. The acceleration value here is how quickly it is able to change the requested output power to the motor. A 1 means it'll go from 0 to 100% in 1 second. 2 means it'll actually go twice as fast as that, which means it'll go from 0 to 100% in half a second. So the bigger this number is, the faster the velocity of the motors can change. So if this is too high, you get jerky motions, which is kind of unstable. If it's too low, it takes forever to get somewhere. So you may want to tweak these based on your drive, the weight of your robot, the RPM of your drive, stuff like that. Drive tolerance is how closely you need to get to your target before the controller says, oh, I'm in position, because we use in position to know when we can move on to the next action. And so this is saying plus or minus half an inch is considered in position. If you let it use the hold time at the end, it'll get closer than that, but it'll still say the whole time that I'm in position. Drive deadband is a bit different. Deadband is when you're within a certain distance, it'll say you're close enough, let's just shut down the motor so that you just don't keep asking for more motion. So this number is in this case 0.2 inches, and it needs to be smaller than the tolerance number, otherwise you'll never get to where you want to be. These can be made bigger or smaller depending on how accurate you want your final motion to be. And finally, the drive max auto. When you issue a drive command, you tell it how fast you want it to get to the point. But the other axes that you're not giving a speed to, they will just default to this maximum. So if we say we're doing a drive command, then it'll use the strafe auto maximum to control the left-right motion, because you're not really giving it a speed for that. It's just using what you've set as the top speed that you're willing to accept for the other motions. Likewise on yaw on rotation. So that's what those are all for. So let's go back. So in the proportional control class, you have a whole bunch of local variables or class variables. And when you create the object with this constructor, you basically pass all those constants in, and they just get loaded into the local variables. So let's look at the get output function. So this is the main method for determining how much output you need for this axis to achieve the requested set point as efficiently as possible. And this is based on the constants you've set beforehand. So let's look at what's happening here. So we call get output to determine what to send to the move robot command. And in this case, we always pass in the current value as the input, which in this case would be a position or an angle. So here's my current position. So the first thing that the code does is it determines the error by subtracting the current position from the desired position, the set point. It also determines the dv, the delta velocity, how much velocity I can change based on my acceleration limit. Strictly speaking, this isn't velocity, but it's treated as velocity by the drive motors, so it's close enough. But we take the acceleration limit, and then we multiply it by how long it's been since the last time we updated it, and that tells us how much we can actually change it this cycle. Then we say, okay, are we in a circular mode? So is this a controller that's controlling a heading angle? Because it needs to make sure the error is within plus or minus 180, so it doesn't get confused about directions and stuff. And then it says, okay, am I in position currently? So it looks at the tolerance that you provided earlier on and compares it with the current error. And if the error is less than the tolerance, it says, oh, I'm in position. So it just sets that flag for you to use later on. But then it gets into the actual calculating of the output. If the error is within the deadband, which are in that tiny little range, then it sets the output to 0. It says, no output, I'm good to go. Otherwise, it says, well, I need to calculate my output. And so it takes the error, multiplies it by the gain, and that's like the highest value that you get as part of this calculation. And then it says, okay, now I need to clip that to my maximum and minimum output limit. I don't want to go above what my limit was set for, so it clips it. And then it says, okay, so that's where I want to be. Can I jump there straight away, or do I have to limit myself based on the acceleration limits that have been placed on me? And so it looks at the difference between the current output and the previous output. Is it greater than that dV we calculated earlier? And if it is, we just don't use the current output. What we do is we take the previous output and add that change to it, the allowable change, and that lets us increase our velocity request at the rate we should based on the acceleration limit. And then we save that as the last output so we can compare it next time. We reset the cycle time so we know how long we've been between cycles, and then we return the output, which then gets used by whoever's running the motors. A couple little functions here. The in position call just returns the internal in position variable. We have a way to get the current set point, same kind of thing. And then we have the reset functions, and there's 3 different versions of this that take different parameters. The most parameters is where we want to reset the control loop, and then we want to set a new set point, and we want to set a power limit for the motion we're requesting. So it saves those things, and then it calls reset down here. We'll get to that. The other method is where we just give it a set point and we don't tell it a power limit, in which case it saves the set point but uses the default power limit that we set in our constants, and then calls reset. And then reset does the actual work. It resets the cycle time clock so that it knows accurately how long it's been since its last run. It sets in position to false because you probably changed the set point or changed the position. So it's like, let's assume nothing. And then it sets the last output to 0. So it basically gets everything ready for the next time get output's going to be called. And there are the functions that we have available there. Back to the top.